Alright guys, so we left off doing the practice table in the lecture slides, the practice table right here. Now we are going to start to talk about electrons. So, electrons, how do they work? We talked a little bit about this on Wednesday, but we still don't really know what they're doing. We know they're sticking around because they love positive charges, but other than that, we don't have a great idea of what they're doing. We had an idea that maybe they were orbiting around the nucleus like the planets around the sun, or that they occupy some space, and we're going to get to our current model of the electron, known as the quantum model. We think of electrons as occupying space around the nucleus. We have our nucleus here, and we can imagine that electrons are occupying in three-dimensional space all around the nucleus, trying to hang out as close as possible to the protons. So, again, we talked about this on Wednesday, how different spaces that these electrons are occupying have different energies. And again, as I get further and further away from the nucleus, my energy becomes greater and greater, and my happiness as an electron goes down. So, we're not going to talk too much about the electron shells, but we're going to make some distinguishing ideas about electrons that are located nice and close to the nucleus versus electrons that are located nice and far from the nucleus. And we're going to call these core electrons versus valence electrons. Now, core electrons, you can imagine your core, your center. We think of core electrons as electrons that are nice and close to the nucleus. They are the lowest energy, meaning they are relaxed because they're sitting pretty next to those protons. They are super happy where they are. Meanwhile, valence electrons are defined. I have two definitions for them. They are in the outermost shells, the outermost area furthest away from the nucleus. They are furthest from the protons, so they're not very happy. They have the highest energy. Now, they consist of unfilled shells, meaning I can add more electrons around as I go. I can add more electrons to this outer valence shell. So, electron configurations would be the next slide. We talk about electron configurations and where electrons are located. We can talk about some atom that has core electrons in the center. The configuration of those would be lower energy, closer to the nucleus, whereas my valence electrons have higher energy and are located further away. So, when I'm talking about core versus valence electrons, the electrons that are going to be important for us this quarter are the valence electrons. We can imagine these core electrons are sitting pretty. They're not moving, they're not doing anything. They are going to sit there and be happy. Meanwhile, my valence electrons, all the way out in the end, they are far away. If I have another, again, this is my positive charge in the center. If I've got another proton out here, positive charge proton, this electron seems to be slightly closer to those protons and might be willing to jump ship to get to the other proton. So these valence electrons are the electrons that are going to be moving around when we are talking about making bonds. These chemical bonds are between valence electrons. So, some cool information about valence electrons is if we look at the periodic table, the number of valence electrons is the same for every single group. Now, a group on a periodic table, grab the periodic table right here. A group on the periodic table is going down a column. Group 1, Group 2, Group 3, Group 4, Group 5, Group 6, Group 7, and Group 8. So Group 1, if you're following along, would start with hydrogen going down. Group 2 would start with Be beryllium, and that's Group 2 going down. Group 3 would start with boron and going down. Group 4 would start with carbon going down. Group 5 with nitrogen going down. Group 6 with oxygen going down. And Group 7 with fluorine going down. Group 8 with helium going down. So each of those groups, and we're kind of ignoring that center. We're going to ignore this whole centerpiece for right now. Just completely ignore it. Those group numbers correspond to the number of valence electrons that we have in this outer shell here. Valence electrons. So for example, hydrogen, we'll draw here, has one valence electron because it's in group 1. Same with lithium, sodium, potassium, rubidium, cesium, francium. Group 1 all have one valence electron. Group 2, starting with beryllium, have 2 valence electrons. Group 2 has 2 valence electrons. Group 3, you can guess, has 3 valence electrons. Group 4 has 4 valence electrons. So carbon has 4 valence electrons. Nitrogen and phosphorus and arsenic and antimony and bismuth all have 5 valence electrons because they are in group 5. Group 6 has 6 valence electrons. Group 7 has 7 valence electrons. Group 8 has 8 valence electrons. And that's kind of a nice way for us to look at the periodic table and say, oh, I know exactly how many electrons every single one of these elements has in its outer shell. Again, these electrons are important because they are the ones located furthest from the nucleus and therefore the ones most likely to participate in any kind of chemical bonding. So, doing the practice, little valence electron practice again. If I point to an element in a group, I will try to get my finger right. Group 1 will have 1 valence electron. Group 2 will have 2 valence electrons, etc., etc., etc. So make sure that you are aware of that. All right. So when we are looking at the periodic table, I've already told you that we have groups. We have groups or families going down. Those are the columns. Meanwhile, we have periods, everything going across. We call a period. So, first period would start at the top with hydrogen going to helium. That is the first period, that's it. Second period starts with lithium and beryllium and goes all the way across to neon. That is the second period. Again, the columns up and down are groups. The periods are across. We have the periodic table also split into little categories called metals, nonmetals, and metalloids. Now, for my purposes, there are actually a couple more groups. The way that I divide the periodic table, and I'm going to get a big one. Here we go, big fancy periodic table. The way that I divide the periodic table here is I say group 1 and group 2 are my true metals, my real metals. They have the properties of metals, and I will read it off for you. The properties of metals include metallic luster. Ooh, they conduct heat and electricity. They are malleable and ductile, meaning they are able to be pulled and stretched or hammered out. Those are metals. Now, the center here, the things that we're used to hearing called metals, right here we have silver and copper and gold and platinum. Those are things that we think of as real metals. Those are called transition metals. So my transition metals are kind of all inside here in the center of the periodic table, my transition metals. All right, so then I have, again, metals, transition metals. Over here I have my non-metals. My non-metals on the other side of the periodic table. So one more time, I have my non-metals, transition metals, and true metals. Now, if you look on your periodic table, unfortunately it's not colored, but we can kind of work with it. If you look at the periodic table that's given to you, we have metals, and the transition metals seem to extend all the way over and to the little ladder of the periodic table. So transition metals, things like lead that are not really in the center, but more kind of near the non-metals underneath the ladder, or the staircase there, is still considered to be transition metals. Once I hit the ladder, those are my metalloids, defined as having properties of both metals and non-metals. And that's kind of where my staircase is. You can see the lighter colors along that staircase. Above the staircase are all of my non-metals. They are defined as having dull luster. They do not conduct electricity, and they are brittle in the solid state. So they are not able to be stretched or hammered out like metals and transition metals. All right, so the last thing that I'm going to talk about today, since we're talking about electrons. Again, we think of the important electrons as being the valence electrons. So my valence electrons are super important. So rather than drawing pictures every time to denote my valence electrons, I'm going to use this thing called Lewis dots. So Lewis dots here are basically just going to represent electrons. If I draw hydrogen, I know that hydrogen has 1 valence electron, the most important electron. It has 1 valence electron because group 1, again, group number means number of valence electrons, and I'm just going to represent that with a dot. That's it, a dot. So, if I have lithium, lithium is also in group 1, meaning it has 1 valence electron. I'm going to represent that one valence electron with a dot. As I go across on the periodic table, I have beryllium next. Be has 2 valence electrons because it is in group 2. Now we remember that electrons love protons, but electrons do not like other electrons. So if I'm going to represent these dots being electrons, then if I have 2 valence electrons, I'm not going to put them next to each other unless I absolutely have to. I will put them apart from each other. So if I move on, beryllium next to boron. Boron now is in group 3. It therefore has 3 valence electrons, so I'm now going to take up even more space. 1, 2, 3 electrons. Now if I go move on to carbon, has 1, 2, 3, 4 electrons, meaning 4 dots, and these are just the Lewis structures of my elements. So carbon, next come nitrogen. I'll put nitrogen up here. Now, my 4 electrons took up all that space. 1, 2, 3, and 4. What I'm going to do now is I have to add 1 more electron, and we think, okay, maybe I can just put it in one of the corners to keep those electrons far away from each other. The maximum number of valence electrons that I'm going to be able to have is 8. If you did not guess that already, again, I have 8 groups. The maximum number I can hold is 8, and each of those electrons, if I have a total of 8, will be paired for some reason that we're not going to go into at all. So once I have 4 electrons by themselves, I'm going to start pairing them. Nitrogen has 5 valence electrons, and that's what its Lewis dot symbol will look like. Next would be oxygen with 1, 2, 3, 4, 5, and 6 valence electrons. In this case, I have 2 paired electrons, so 4 total pairs, so 2 pairs of electrons and 2 unpaired electrons. Next would be fluorine, where I have 1, 2, 3, 4, 5, 6, 7 valence electrons. 7 valence electrons, 3 pairs, and 1 unpaired electron. If I move on, I finish with neon. Neon, which is in group 8. Group 8 has 8 valence electrons. It will be completely full. What we call this is a full valence shell. Full valence shell. Now, we look at group 8, and group 8 is actually really special. They are called something like the noble gases. Now, the reason they're so noble is because they have a full valence shell. Now, that's kind of special, and we're not going to talk much about why that is, but it is good to note that they have a full valence shell. So those electrons on the very outermost shell, furthest from the nucleus, they're full. And that's basically why the noble gases are so noble. So, with that in mind, we're going to save the rest of this for Monday. And see you all then. Have a great weekend.